Hello, this is Harrison Moore, and this is Lab 3, Black Holes and Orbits. Purpose of this lab is, in part 1, to analyze the motion of a star to determine the mass of a black hole, and then in part 2, to simulate the motion of a spaceship around a planet and its moon by calculating necessary gravitational forces. Some important principles we'll find are the change of momentum is equal to mass times the change of velocity. That's important when we know that F net is equal to the change of momentum over change in time. So therefore, F net is equal to mass times the change of velocity over change in time. Furthermore, F net is equal to F net parallel plus F net perpendicular. The gravitational constant is equal to G times the mass of the first objects times the mass of the second object, all over the distance between the two objects squared. Um, Velocity final is equal to velocity initial plus F net over m times delta t, and position final is equal to position initial plus velocity plus change in time. So first off, the code for the black hole mass. This is F net is equal to the change in momentum times change in time. And then here's F net parallel, and then the final box is F net perpendicular. Here are the results. The star started here. The black is the black hole, and it went in a circular pattern. As it got closer, you can see that it kind of went elliptical because the potential gravity is higher the closer it gets to the object. So therefore, the kinetic energy is also higher. I found that my F net is equal to 9.86 E28 newtons, and the mass of my black hole is 1.42 E34 kilograms. Here's my don't crash code. Here's all the just R hats and forces and positions, and then here is the moon velocity and the ship velocity, as well as their positions. And here are my results. I found it really, really difficult to get an initial velocity to make a perfect figure eight. This was kind of the best I could do after a lot of trial and error. My speed was 17,500 in the x direction and 5,000 in the y direction, and that is in meters per seconds. So some of the possible errors that I could have run into were first accuracy. I used trial and error to find the velocities in part 2, which isn't the most exact science. I could have spent more time to get a really exact number. As you can see here, both my numbers are both zeros in the last two. If I really wanted to spend more time and find an exact number, I could have gone and delved deeper into that. Secondly, approximation. This isn't exact. The Glow script isn't exactly perfect because the simulation, we were assuming that there was no external forces acting on the object, which in space that's fair, but you never know if there's another star or planet that has gravitational force on the ship or the moon. Finally, how the net force in its parallel and perpendicular components are different from the rate of change of momentum in its parallel and perpendicular components. Mathematically, they're the same. However, the momentum change rate is much easier to calculate. To find net force, you need to find every external factor affecting the system, whereas for the rate of change of the momentum, you only need the change of velocity. Secondly, this imaginary system has a black hole, a star, a planet, and a moon. If you wanted to predict the motion of the entire system, what would you need to include in your computational model? You would need to consider all the parts of the surroundings that are acting on the system in any way, and vice versa. There would be dominant forces between the star, moon, and black hole. That is all. Thank you so much for your time. Bye-bye.